What if the most important archaeological discoveries of the 21st century aren't buried in Earth's soil, but tumbling through space above our heads? For most of human history, we assumed Earth existed in splendid isolation, separated from other worlds by distances so vast that meaningful interstellar findings were impossible. Then, in 2017, something tumbling through space at 87,000 kilometers per hour shattered that assumption forever. It was followed by others, each more mysterious than the last. These interstellar visitors don't behave like anything in our solar system. They accelerate without visible propulsion. They maintain structural integrity across million-year journeys. They arrive from random directions with such frequency that statisticians are starting to question the laws of probability themselves. Tonight, as 3I-ATLAS reaches its closest approach to the Sun, we'll discover why this visitor transforms Oumuamua from a cosmic anomaly into the first piece of a much larger puzzle. Before we journey through this cosmic mystery together, let me know down below where in the world you're listening and what time it is for you right now. And if you genuinely enjoy what I do here, consider subscribing for a nightly dose of deep space mysteries. Now, prepare yourselves. We begin. Picture this. It's midnight at the Haleakala Observatory in Hawaii. The only sounds are the gentle hum of cooling fans and the soft click of hard drives processing terabytes of star data. Astronomers peer into screens showing nothing but tiny points of light against the infinite black. Then something moves, something that shouldn't be there. Most nights, the universe follows predictable patterns. Stars hold their positions. Planets trace their ancient paths. Even asteroids and comets dance to gravitational rhythms that have remained unchanged for billions of years. But on October 19th, 2017, the cosmos delivered something entirely different. Something that would rewrite our understanding of what travels between the stars. The Pan-STARRS telescope captured a single frame that changed everything. A pinpoint of light, moving faster than it had any right to move, tracing a path that defied the fundamental laws of celestial mechanics. This wasn't following the sun's gravitational embrace like every other object in our solar system. This visitor was passing through, as if it had somewhere else to be. Within hours, calculations revealed the impossible. The object's trajectory was hyperbolic, not the gentle ellipse of a comet or asteroid, but the sharp curve of something that came from elsewhere and was heading elsewhere still. Its speed relative to the Sun was 26 kilometers per second, faster than anything born in our stellar neighborhood should travel. The astronomical community erupted into controlled chaos. Emergency observation requests flooded telescope networks worldwide. Everyone wanted a piece of this cosmic anomaly before it vanished forever into the darkness between stars. Social media exploded with speculation. News anchors stumbled over its Hawaiian name, Oumuamua, meaning scout or messenger from afar arriving first. But here's where the story gets interesting. As telescopes around the world turned their attention to this interstellar visitor, they discovered something that challenged every assumption about what such objects should look like. This wasn't the roughly spherical chunk of rock and ice they expected. The brightness of Oumuamua varied by a factor of 10 as it tumbled through space, suggesting an elongated shape unlike anything we'd ever encountered. Imagine a cosmic cigar, perhaps 800 meters long, but only 80 meters wide, spinning end over end like a discus thrown by an invisible giant. Its surface reflected sunlight in ways that suggested either an extremely unusual composition or an artificial origin. Some scientists whispered what others dared not say aloud. What if this wasn't natural at all? The questions multiplied faster than answers. How could an object survive the journey between stars without being torn apart by cosmic radiation and micrometeorite impacts? Why was it shaped so strangely? And most puzzling of all, why did it seem to accelerate slightly as it moved away from the sun? despite showing no signs of the gas jets that typically produce such effects in comets. Dr. Robert Werrick, the astronomer who first spotted the anomaly, later described the moment of discovery. "You look at the data, and you think the computer made an error. Objects just don't move like this in our solar system." But the computer hadn't made an error. The universe had delivered something unprecedented. As Oumuamua tumbled away from the sun, picking up speed as it departed, it left behind more questions than answers. Was this visitor a fragment of some distant world, ejected billions of years ago by gravitational chaos around an alien star? Or was it something else entirely, a piece of technology designed by minds we couldn't yet comprehend? The scientific establishment quickly rallied around natural explanations. Comets get ejected from their parent systems all the time. Gravitational interactions with giant planets can fling smaller objects into interstellar space at tremendous velocities. What we witnessed was probably just the first time we'd been lucky enough to catch one of these cosmic refugees passing through our neighborhood, but luck seemed an inadequate explanation for the timing. Humanity had been systematically scanning the skies for less than a century. The odds of detecting such a rare visitor during this brief window of our technological adolescence seemed almost impossibly small. Unless, of course, these visitors weren't as rare as we assumed. While Oumuamua accelerated beyond the reach of our most powerful telescopes, something fundamental had shifted in astronomy. Survey programs began devoting more time to searching for similar objects. New detection algorithms were developed specifically to spot the telltale signatures of interstellar motion. Funding committees, previously skeptical of exotic research proposals, suddenly found themselves approving projects dedicated to studying visitors from beyond our solar system. The universe had shown us something we weren't prepared to see. An object that belonged to no star system, following no familiar orbit, exhibiting properties that strained our understanding of natural processes. It arrived unannounced, revealed its secrets reluctantly, and departed with the same mysterious purpose that brought it here. As Oumuamua faded into the cosmic dark, traveling towards the constellation Pegasus at 38 kilometers per second, it left humanity with a sobering realization. We are not alone in the space between stars. Objects, natural or otherwise, drift through the galactic void, carrying with them the stories of distant worlds and ancient catastrophes. The messenger from afar had delivered its message, though we were still learning how to read it. What seemed certain was that Oumuamua would not be the last of its kind. The space between stars was not the empty void we'd imagined, but a highway travelled by wanderers from every corner of the galaxy. And if chunks of rock and ice could survive such journeys, what else might be out there, drifting between the stars, waiting for the right moment to pass through our cosmic backyard? The question hung in the air, like the scent of rain before a storm, electric with possibility. As one astronomer put it, "We've been looking up at the stars our entire history, thinking we were alone in this corner of space. Now we know better. The galaxy has been watching us all along, sending its messengers when we were finally ready to notice them." The age of interstellar visitors had begun. Part 2. The Day the Sky Changed. Oumuamua's First Glimpse. The transformation of our understanding didn't happen gradually. It occurred in a single moment, captured by a robotic telescope on a mountain in Hawaii, processed by algorithms that had been running the same calculations for years. October 19th, 2017, 2:22 a.m. local time. The Pan-STARRS 1 telescope on Haleakala completed another routine scan of a patch of sky in the constellation Cancer. The image contained roughly 60 zero stars, most of them so distant that their light had travelled for millions of years to reach this moment. Among these ancient photons was something else entirely. A tiny streak of reflected sunlight from an object that had never belonged to our Sunday. the discovery almost didn't happen. The automated detection software flagged the object as a probable near-Earth asteroid, nothing unusual in itself. Our solar system is littered with rocky debris left over from its formation 6 billion years ago. Most of these objects follow predictable elliptical orbits, occasionally drifting close enough to Earth to warrant attention from planetary defense programs. But Dr. Robert Werrick, reviewing the night's data at the University of Hawaii, noticed something odd. The object was moving too fast and in the wrong direction. Initial calculations suggested it was approaching from outside the solar system, a possibility so unlikely that most astronomers would have assumed a computational error. The object was designated A 2017 Uon, a temporary label that revealed nothing of its extraordinary nature. Within 48 hours, additional observations confirmed the impossible. This visitor was following a hyperbolic trajectory with an eccentricity greater than 1.0. In the language of orbital mechanics, this meant it was unbound to the Sun's gravity, merely passing through on its way to somewhere else. The astronomical community responded with unprecedented urgency. Emergency observation requests were submitted to every major telescope facility on Earth. Time normally allocated to long-term research projects was hastily reassigned to track this cosmic interloper before it disappeared forever. The Hubble Space Telescope, the Very Large Telescope in Chile, the Gemini Observatory, all focused their attention on a visitor that would be visible for mere weeks. What they discovered challenged fundamental assumptions about the nature of interstellar objects. Traditional models predicted that debris ejected from other star systems would resemble the comets and asteroids of our own solar system, roughly spherical, composed of familiar mixtures of rock and ice, perhaps a few kilometers in diameter. Oumuamua fit none of these expectations. Its brightness varied by a factor of 10 over an 8-hour rotation period, suggesting an extremely elongated shape. The most likely explanation was a cigar-shaped object roughly 800 meters long and 80 meters wide, an aspect ratio unlike any natural object ever observed in our solar system. The stranger it became, the more urgent the observations grew. Ground-based telescopes tracked it continuously, measuring its rotation, composition, and trajectory with unprecedented precision. Radio telescopes listened for any possible artificial signals. Even SETI researchers joined the effort, though they found only the silence of interstellar space. Then came the acceleration anomaly. As Oumuamua moved away from the Sun, it began to speed up slightly, not dramatically, but enough to be measurable by precise astrometric observations. This non-gravitational acceleration is common among comets, caused by jets of gas sublimating from their surfaces as they warm up near the sunday. But Oumuamua showed no signs of such outgassing. No visible coma, no tail, no spectroscopic evidence of water vapor or other volatiles. The mystery deepened with every measurement. Its surface appeared unusually red in color, suggesting organic compounds that had been bombarded by cosmic rays for millions of years. Yet despite this ancient patina, the object seemed structurally intact, showing no signs of the fracturing and erosion expected from eons of interstellar travel. Dr. Alan Fitzsimmons from Queen's University Belfast captured the scientific community's bewilderment. Every time we pointed a new instrument at this thing, it became stranger. We kept expecting it to behave like a normal comet or asteroid, but it refused to follow the script. The media response was immediate and intense. Within days, Oumuamua appeared on front pages worldwide. Speculation ranged from the scientifically plausible to the wildly imaginative. Was this a fragment of an exoplanet blasted into space by some cosmic catastrophe? Could it be an alien artifact deliberately sent to study our solar system? Or was it simply a type of object so rare that we'd never encountered one before? The scientific establishment urged caution, emphasizing the importance of extraordinary evidence for extraordinary claims. Natural explanations, while admittedly incomplete, remained more plausible than artificial ones. Perhaps Oumuamua was composed of unusual materials that explained its strange properties. Maybe it was a fragment of a larger object that had been shaped by eons of cosmic collisions. But questions persisted. If interstellar objects were common, why had we never detected one before? Our asteroid and comet surveys had been operating for decades, cataloguing hundreds of thousands of solar system objects. The probability of finally encountering an interstellar visitor seemed almost impossibly small, unless such objects were far more numerous than anyone had predicted. The implications were staggering. If Oumuamua was typical of interstellar debris, then our solar system was constantly being visited by fragments from other star systems. We existed within a vast river of cosmic material, most of it too small or distant to detect with current technology. Every year, perhaps every month, pieces of alien worlds might be passing through our cosmic neighborhood, carrying with them the chemical signatures and physical properties of their birthplaces. As Oumuamua continued its journey toward the constellation Pegasus, accelerating beyond the reach of Earth's most powerful telescopes, it left behind a transformed scientific landscape. Funding agencies suddenly found themselves supporting research into interstellar object detection. New survey telescopes were designed with the specific goal of finding and tracking visitors from other star systems. The visitor had spent just 11 weeks under intense scientific scrutiny before fading into the cosmic background. In that brief window, it managed to challenge our understanding of planetary formation, interstellar chemistry, and the frequency of material exchange between star systems. It demonstrated that the space between stars was not the empty void we'd imagined, but a complex environment populated by wanderers from every corner of the galaxy. Perhaps most importantly, Oumuamua proved that we were not as isolated as we'd believed. The solar system was not a closed system, protected from outside influence by the vast distances between stars. We were participants in a galactic ecosystem, receiving visitors and presumably contributing our own debris to the interstellar medium. As the object disappeared beyond the orbit of Jupiter, travelling at 38 kilometers per second relative to the Sun, one fact became clear. Oumuamua was probably not unique. If the galaxy contained billions of planetary systems, each occasionally ejecting material into interstellar space, then such visitors might be more common than we'd ever imagined. The sky had not just changed on October 19, 2017. Our entire understanding of our place in the cosmos had shifted. We were no longer alone in this corner of space, waiting patiently for signals from distant civilizations. The universe was actively delivering samples to our doorstep, carrying messages written in the language of physics and chemistry rather than radio waves. The first interstellar visitor had departed, but its legacy remained. Somewhere in the darkness beyond Pluto's orbit, Oumuamua continued its billion-year journey to the stars, carrying with it our questions and our newfound humility about what else might be travelling through the space we call empty. Part 3. The impossible shape. The numbers didn't make sense. That was the first thing every astronomer noticed when they tried to model Oumuamua's extraordinary light curve. Objects in space typically vary in brightness by perhaps 20 or 30% as they rotate, showing us their different faces as they tumble through the void. But this interstellar visitor was playing by different rules entirely. Every 26 hours, Oumuamua would dim to nearly invisible, then brighten to 10 times that level, then fade again with mechanical precision. This wasn't the gentle fluctuation of a potato-shaped asteroid, or the irregular blinking of a fractured comet. This was the signature of something fundamentally different, an object so elongated that it seemed to challenge the basic physics of how celestial bodies form and survive. Dr. Karen Meach from the University of Hawaii led the international team trying to make sense of these observations. When we first saw the light curve, she recalls, several people suggested there must be an error in the data reduction. Objects just don't naturally form with aspect ratios this extreme. The most conservative estimates suggested Oumuamua was at least 6 times longer than it was wide. More aggressive interpretations of the data pushed this ratio even higher, perhaps 10 to 1, making it more like a cosmic needle than a conventional space rock. To put this in perspective, imagine a football field that was only 10 yards wide. No known process in planetary science could explain how such an object might form, let alone survive the violent journey between star systems. The rotation itself presented another puzzle. Most asteroids and comets spin around their shortest axis, like a top spinning on a table. It's the most stable configuration, the natural result of countless collisions over millions of years. But Oumuamua was tumbling in a complex pattern that astronomers call non-principal axis rotation, essentially doing cosmic gymnastics as it moved through space. This tumbling motion suggested either a recent collision that had disrupted its rotation or an internal structure unlike anything in our experience. Perhaps it was hollow. Perhaps it was composed of materials with unusual density distributions. Or perhaps it had been artificially constructed with a specific purpose in mind. The surface properties only deepened the mystery. Spectroscopic analysis revealed a dark, reddish coloration consistent with organic compounds that had been irradiated by cosmic rays for millions of years. This supported the idea that Oumuamua was ancient, possibly older than our solar system itself. Yet, despite this apparent age, the object showed no signs of the structural degradation expected from eons of micrometeorite bombardment and cosmic ray exposure. More puzzling still was its thermal behavior. As Oumuamua approached the Sun, it should have warmed up significantly, potentially causing ice to sublimate and creating the characteristic coma and tail of an active comet. Instead, it remained stubbornly inert, showing no signs of outgassing despite reaching temperatures that should have vaporized any volatile materials on its surface. Then came the acceleration anomaly that transformed scientific curiosity into genuine bewilderment. Precise measurements of Oumuamua's trajectory revealed that it was speeding up as it moved away from the Sun, not dramatically, but by about 0.25 millimeters per second squared. For a comet, such acceleration would be easily explained by gas jets created by sublimating ice, but Oumuamua showed no evidence of such outgassing. The effect was small but undeniable, measured independently by multiple tracking stations around the world. Whatever was pushing Oumuamua away from the Sun was doing so invisibly, without any of the telltale signs that accompany natural cometary activity. Dr. Marco Micheli from the European Space Agency, who led the orbital analysis, described the dilemma: we're seeing an acceleration that requires some kind of force, but we can't identify the mechanism. It's like watching a car speed up without being able to see the engine. Theoretical explanations multiplied like cosmic conspiracy theories. Perhaps Oumuamua was venting gas so tenuous that it couldn't be detected by our instruments. Maybe it was composed of exotic materials that responded to solar radiation in unexpected ways. Some suggested it might be a hydrogen iceberg, a chunk of solid hydrogen that would sublimate invisibly as it warmed up. More exotic proposals emerged from the scientific fringe. Could this elongated object be a light sail designed by an extraterrestrial civilization to ride the pressure of starlight between stellar systems? The acceleration was consistent with what would be expected from such a device, and the extreme aspect ratio would maximize the surface area exposed to solar radiation. Dr. Avi Loeb from Harvard University became the most prominent advocate of this artificial hypothesis, arguing that the scientific community was too quick to dismiss technological explanations. When we encounter something unprecedented, he argued, we should consider all possibilities, including those that challenge our preconceptions about what exists in the universe. The debate revealed deeper tensions within the astronomical community. Traditional scientific methodology demands extraordinary evidence for extraordinary claims, and the evidence for an artificial origin remained circumstantial at best. Most researchers preferred to exhaust natural explanations before entertaining more speculative alternatives. Yet, the natural explanations strained credibility in their own ways. The proposed mechanisms for Oumuamua's acceleration required fine-tuned parameters and unusual material properties. The object would need to be composed of materials that had never been observed in our solar system, structured in ways that defied conventional understanding of how celestial bodies form. As Oumuamua faded beyond the detection limits of Earth's telescopes, it left behind a catalogue of unanswered questions. How could an object maintain such an extreme shape without flying apart under the stress of its own rotation? What invisible force was accelerating it away from the Sun? And perhaps most importantly, how many similar objects might be passing through our solar system undetected? The visitor had provided humanity with its first close look at material from another star system, and that material refused to behave according to the rules we thought governed the universe. It was too elongated, too stable, too mysterious to fit comfortably into existing categories of astronomical objects. In the months following Oumuamua's departure, computer simulations attempted to model its formation and evolution. Researchers proposed scenarios involving tidal disruption near massive stars, collisional fragmentation in dense stellar clusters, and exotic sublimation processes that could produce such unusual shapes. None of these models provided a completely satisfying explanation for all of the object's observed properties. The most honest assessment came from Dr. Robert Werrick, the astronomer who first discovered the object. We've learned more about interstellar visitors from this single object than from decades of theoretical speculation. But mostly, what we've learned is how much we don't know. As Oumuamua continued its journey toward the constellation Pegasus, tumbling through interstellar space at nearly 40 kilometers per second, it carried with it our assumptions about what natural objects should look like. The messenger from beyond our solar system had delivered a clear message. The universe is stranger than we imagined, populated by objects that challenge our understanding of physics, chemistry, and perhaps even the definition of natural versus artificial. The impossible shape had forced us to confront the possibility that our corner of the galaxy was not as isolated or as typical as we'd assumed. If this was what interstellar visitors looked like, then we were clearly unprepared for what else might be travelling through the space between stars. The cosmic cigar had tumbled away into darkness, leaving behind more questions than answers and a scientific community humbled by its first encounter with truly alien matter. Part 4. A New Cosmic Era. Preparing for the next visitor. The scientific community's response to Oumuamua was swift and decisive. Within months of the visitor's departure, astronomy underwent a quiet revolution that would reshape how we scan the skies and interpret what we find there. Emergency meetings convened at observatories worldwide. Funding committees that had previously dismissed interstellar object research as too speculative suddenly found themselves approving multi-million-dollar projects. The message was clear. We had been caught unprepared for our first confirmed interstellar visitor, and we couldn't afford to make the same mistake twice. The Catalina Sky Survey in Arizona immediately reconfigured its search algorithms. Software that had been optimized to find Earth-threatening asteroids was reprogrammed to detect the subtle signatures of hyperbolic orbits, the mathematical fingerprints of objects that originated beyond our solar system. Similar upgrades were implemented at the LINEAR program in New Mexico and the NEOWISE Space Telescope, but the most ambitious response came from the Vera C. Rubin Observatory, then under construction in Chile. Originally designed to create the most detailed map of the universe ever attempted, the project's scope was quietly expanded to include a dedicated search for interstellar objects. When operational, the observatory would scan the entire visible sky every few nights, generating terabytes of data that would be sifted by artificial intelligence systems specifically trained to recognize visitors from other star systems. Dr. Mario Jurich from the University of Washington, who led the Rubin Observatory's data management efforts, explained the magnitude of the challenge. We're talking about finding needles in a haystack the size of the observable universe. But Oumuamua taught us that these needles exist, and they're passing through our cosmic neighborhood more often than we ever imagined. The urgency was justified by simple mathematics. If Oumuamua was representative of a larger population of interstellar objects, then our solar system should be visited by dozens or even hundreds of similar objects each year. Most would be too small or distant to detect, but a significant fraction should be within reach of next-generation survey telescopes. Previous estimates had predicted maybe one detectable interstellar visitor per decade, a rate so low that most astronomers considered it a theoretical curiosity rather than an observational priority. But Oumuamua's appearance suggested these estimates were wrong by orders of magnitude. The space between stars appeared to be far more crowded than anyone had suspected. International cooperation accelerated dramatically. The European Space Agency fast-tracked development of the Gaia mission's successor, designed to map stellar motions with unprecedented precision. NASA's Planetary Defense Coordination Office expanded its mandate to include tracking and characterizing interstellar objects. Even amateur astronomers were recruited into the effort with new software tools that would allow backyard telescopes to contribute to the search. The technological challenges were immense. Interstellar objects move differently from anything else in the solar system, following hyperbolic paths that carry them from interstellar space back to interstellar space in a matter of months. Detection windows are brief, sometimes lasting only weeks between when an object becomes bright enough to spot and when it fades beyond the reach of follow-up observations. New artificial intelligence systems were developed specifically to recognize these unusual motion patterns in real time. Machine learning algorithms trained on simulated interstellar visitors learned to distinguish them from the much more numerous population of conventional asteroids and comets. The goal was to identify promising candidates within hours of their first detection, allowing telescopes worldwide to immediately begin detailed observations. Perhaps more importantly, the scientific community began preparing for the next visitor's arrival. Oumuamua had caught astronomers off guard, forcing them to scramble for telescope time and coordinate observations with little advance notice. Future discoveries would trigger predetermined response protocols with pre-allocated observation time at major facilities and streamlined procedures for international coordination. The lessons learned were sobering. Oumuamua had been visible for only 11 weeks before fading below the detection threshold of Earth's most powerful telescopes. In that brief window, astronomers had managed to measure its basic properties: size, shape, composition, and trajectory. But many fundamental questions remained unanswered. The object's internal structure, detailed composition, and formation mechanism were still mysteries. Future visitors would be studied far more intensively. Plans were developed for rapid response spectroscopy, radar imaging, and even potential space missions to intercept particularly interesting objects. The Japanese Space Agency began preliminary studies of modified solar sail technology that could potentially chase down interstellar visitors, while NASA's Jet Propulsion Laboratory investigated whether existing spacecraft could be redirected to study such objects. The search expanded beyond traditional optical telescopes. Radio astronomers developed new techniques to detect the subtle signature of outgassing that might be invisible to conventional instruments. Infrared surveys were optimized to spot the thermal emission of interstellar objects that might be too dark to detect in visible light. Even gravitational wave detectors were considered as potential tools for finding very massive interstellar objects. The implications extended far beyond astronomy. If interstellar objects were common, they represented a previously unknown mechanism for material transport between star systems. Complex organic molecules, and perhaps even primitive life forms, might survive the journey between stars within protective rocky or icy matrices. The concept of panspermia, the idea that life might spread throughout the galaxy via natural processes, suddenly seemed far more plausible. Astrobiologists began developing protocols for analyzing future interstellar visitors for signs of biological material. Sterile sample collection procedures were designed for potential space missions, while ground-based spectroscopy programs searched for the signatures of organic compounds that might indicate biological origin. The search for extraterrestrial intelligence also evolved in response to Oumuamua. SETI researchers realized that technological civilizations might prefer to communicate through physical artifacts rather than radio signals. Interstellar space might be filled with mechanical messengers, carrying information encoded in their structure, composition, or trajectory. New listening protocols were developed to scan interstellar visitors for any possible artificial signals. Radio telescopes would automatically target newly discovered objects, searching for the patterns that might indicate technological origin. Even optical telescopes began looking for unusual reflectivity patterns that might suggest artificial surfaces or structures. The transformation was remarkable to witness. A scientific discipline that had been largely theoretical suddenly became intensely observational. Researchers who had spent careers modeling the hypothetical properties of interstellar objects found themselves analyzing real data from an actual visitor. The field of interstellar object science had been born overnight, complete with dedicated conferences, specialized journals, and career paths for young researchers. As the months passed following Oumuamua's departure, the scientific community settled into a new routine of vigilant watching. Every night, automated telescopes scanned predetermined patches of sky, their data feeds monitored by algorithms trained to recognize the motion patterns of interstellar interlopers. The discovery of the next visitor was not a question of if, but when. Behind the technological preparations lay a deeper philosophical shift. Humanity's relationship with the cosmos had been fundamentally altered by our first confirmed encounter with material from another star system. We were no longer passive observers of a distant universe, but active participants in a galactic ecosystem that occasionally delivered samples to our doorstep. The age of interstellar archaeology had begun. Each future visitor would carry with it the chemical and physical signatures of its birthplace, fragments of alien worlds that had been ejected into the void by gravitational interactions, stellar explosions, or cosmic collisions. By studying these cosmic refugees, we would gradually piece together the story of planetary formation and evolution throughout the galaxy. The stage was set for the next act in humanity's expanding awareness of its cosmic context. Telescopes watched, algorithms waited, and somewhere in the darkness between stars, the next messenger was already on its way. Part 5. Enter 3I-ATLAS. The second messenger, July 1st, 2025. The ATLAS telescope at Rio Hurtado, Chile, was conducting its nightly survey of the southern sky when its automated detection system flag something unusual moving against the star-rich backdrop of Sagittarius. The object was faint, barely distinguishable from the background noise, but its motion was unmistakable, too fast and in the wrong direction to be a conventional solar system resident. Dr. Larry Deno, the ATLAS principal investigator at the University of Hawaii, received the automated alert at 3:47 a.m. local time. After years of scanning the skies for potentially hazardous asteroids, his team had developed an intuitive sense for what belonged in the solar system and what didn't. This object, designated C 2025 None, ATLAS, definitely didn't belong. The preliminary orbital calculations were completed within 6 hours of discovery. The results sent a wave of excitement through the global astronomy community. Eccentricity approximately 6.0, indicating an extremely hyperbolic orbit that originated far beyond the Sun's gravitational influence. The object was approaching from the direction of Sagittarius at a relative velocity of roughly 61 kilometers per second, making it the fastest confirmed interstellar visitor ever detected. What made this discovery particularly significant was its timing. Unlike Oumuamua, which had been spotted during its departure from the inner solar system, 3I-ATLAS was caught during its approach. Astronomers would have months, rather than weeks, to study this cosmic wanderer before it reached closest approach to the Sun and began its journey back to interstellar space. The object's designation followed established protocols. C indicated a comet 2025 None, marked it as the first object discovered in the second half of July 2025, and ATLAS credited the discovering survey. The 3I prefix would come later, officially designating it as the third confirmed interstellar object after 1I, Oumuamua, and 2I, Borisov. But 3I-ATLAS was already displaying characteristics that set it apart from its predecessors. Even at a distance of 5 astronomical units from the Sun, roughly the orbital distance of Jupiter, the object showed clear signs of activity. A faint coma of gas and dust surrounded the nucleus, extending roughly 25 kilometers into space. This early outgassing suggested a composition rich in volatile materials that sublimated readily as the object warmed during its approach to the inner solar system. The Gemini North telescope on Mauna Kea was the first to capture detailed images of the new arrival. The high-resolution photographs revealed a compact, fuzzy object with a short, stubby tail pointing away from the sunday. Unlike the smooth, star-like appearance of Oumuamua, 3I-ATLAS looked unmistakably comet-like, conforming more closely to theoretical predictions of what interstellar objects should resemble. Within 48 hours of the discovery announcement, the object became the most intensively studied comet in history. The European Southern Observatory's Very Large Telescope in Chile began spectroscopic observations to determine its chemical composition. The Hubble Space Telescope was hastily reprogrammed to capture the highest resolution images possible of the visitor's nucleus and coma. Radio telescopes around the world listened for any possible signals that might indicate artificial origin. The scientific response was dramatically different from the chaotic scramble that had followed Oumuamua's discovery. Years of preparation paid off as predetermined observation protocols activated automatically. Emergency telescope time had been pre-allocated specifically for interstellar visitors. International coordination proceeded smoothly through established channels. The astronomical community was ready this time. Dr. Robert Werrick, who had discovered Oumuamua 8 years earlier, reflected on the difference. We learned our lesson from the first visitor. This time we had plans, protocols, and prepared instruments. Instead of playing catch-up, we were actually ahead of the game. Initial spectroscopic observations revealed a surface composition dominated by silicate minerals and organic compounds, similar to comets that originated in the outer regions of our own solar system. But subtle differences in isotope ratios hinted at a formation environment unlike anything found in our cosmic neighborhood. The object carried chemical signatures of a star system with different metallicity and stellar evolution history than our Sunday. The rotation period was measured at approximately 29 hours, considerably slower than Oumuamua's 8-hour tumbling motion. Light curve analysis suggested a more conventional shape, roughly spherical or modestly elongated, without the extreme aspect ratio that had made its predecessor so controversial. In many ways, 3I-ATLAS looked exactly like what astronomers had expected interstellar visitors to resemble, but appearances could be deceiving. As the object continued its approach toward the Sun, scheduled to reach perihelion at 1.4 astronomical units on October 30th, 2025, its behavior began to reveal unexpected complexities. The rate of outgassing varied in patterns that didn't correlate simply with solar heating. Spectral lines appeared and disappeared as different chemical compounds sublimated from the surface. The tail structure showed subtle asymmetries that suggested complex rotation or internal structure. The discovery had profound implications for our understanding of interstellar object populations. Finding 2 such visitors within 8 years suggested they were far more common than previously believed. Statistical analyses based on detection rates and survey capabilities indicated that similar objects might pass through the inner solar system several times per decade. More intriguingly, 3I-ATLAS approached from a completely different direction than Oumuamua. While the first interstellar visitor had entered from the direction of Vega, in the constellation Lyra, this new arrival came from Sagittarius, roughly 90 degrees away on the sky. The implications were staggering. Interstellar space was not only populated by such objects, but they arrived from all directions, suggesting a truly galactic population of wandering debris. The object's high velocity also raised questions about its origin. At 61 kilometers per second relative to the Sun, it was moving significantly faster than would be expected for objects ejected by normal planetary interactions. Such extreme velocities suggested either a very energetic ejection mechanism, perhaps involving stellar explosions or close encounters with massive objects, or a very distant origin that allowed gravitational acceleration over vast distances. Computer simulations began tracing possible trajectories backward through time, attempting to identify the object's stellar birthplace. The calculations were complicated by the gravitational influences of countless stars encountered during what might have been millions or billions of years of interstellar travel. But preliminary results suggested origins in the galactic thick disk, possibly ejected from a planetary system that had been destabilized by stellar evolution or gravitational chaos. The media response to 3I-ATLAS was notably more measured than the sensationalism that had surrounded Oumuamua. The scientific community had learned to emphasize natural explanations while acknowledging the profound implications of routine interstellar visitors. Headlines focused on the object's pristine composition and the opportunity to study material from another star system, rather than speculation about alien technology. Yet beneath the scientific excitement lay a growing realization of just how connected our solar system was to the broader galaxy. These weren't random encounters with cosmic debris. They were regular deliveries of samples from distant worlds, each carrying information about conditions in star systems we might never visit directly. As 3I-ATLAS continued its approach through the asteroid belt, brightening steadily as solar heating increased its outgassing activity, it carried with it the accumulated wisdom of another star system. Its chemical composition told the story of planetary formation around a different type of star. Its isotope ratios revealed details about stellar nucleosynthesis processes that had occurred before our Sun was even born. The second messenger had arrived, and this time we were ready to listen. Part 6. The Path of the Outsider. The trajectory of 3I-ATLAS told a story written in the language of mathematics and gravity, a narrative that stretched across millions of years and countless light-years of interstellar space. To understand where this cosmic wanderer was heading, astronomers first had to trace where it had been, a detective story played out across the galaxy. Unlike the familiar elliptical orbits of planets and comets bound to our Sun, 3I-ATLAS followed a hyperbolic path with an eccentricity of approximately 6.0. In orbital mechanics, any eccentricity greater than 1. 0 indicates an unbound trajectory, the mathematical signature of an object that arrived from interstellar space and would return there after its brief encounter with our solar system. The object's closest approach to the Sun, scheduled for October 30th, 2025, would bring it to within 1.4 astronomical units of our star, roughly the orbital distance of Mars. This was close enough to provide excellent observation opportunities while remaining far enough away to avoid the extreme heating that might completely vaporize its nucleus. Its closest approach to Earth would occur slightly earlier, at a safe distance of approximately 1.6 to 1.8 astronomical units, but it was the direction of 3I-ATLAS's approach that revealed the most fascinating details about its cosmic journey. The object entered our solar system from the constellation Sagittarius, moving at an angle nearly perpendicular to the plane of planetary orbits. This side-on approach was unusual among known interstellar objects and provided important clues about its origin and the structure of the local galactic environment. Computer simulations traced the object's trajectory backward through time, attempting to identify its stellar birthplace. The calculations required accounting for the gravitational influences of every star within several hundred light-years of our solar system, a computational challenge that pushed the limits of even the most powerful astronomical supercomputers. The most likely scenario placed 3I-ATLAS's origin in the galactic thin disk, possibly ejected from a planetary system sometime between 1 and 10 million years ago. The ejection mechanism could have been a gravitational interaction with a giant planet, similar to how Jupiter occasionally flings comets out of our own solar system. Alternatively, the object might have been liberated during the death throes of its parent star, blasted into interstellar space by stellar winds or more violent processes. Dr. Fabo Fung from the University of Hertfordshire, who led one of the trajectory reconstruction efforts, described the challenge. We're trying to solve a cosmic murder mystery where the crime scene is millions of years old and scattered across hundreds of light years. Every star in the neighborhood is a potential suspect, and the evidence has been corrupted by eons of gravitational interference. The object's extreme velocity, 61 kilometers per second relative to the Sun, provided additional clues about its violent past. Such speeds required either a very energetic ejection process or acceleration over vast distances and enormous periods of time. The former might indicate ejection during a stellar explosion or close encounter with a massive object like a black hole. The latter suggested an origin so distant that gravitational interactions with multiple stellar systems had gradually accelerated the object to its current velocity. Comparing 3I-ATLAS to its predecessors revealed the diversity of interstellar visitors. While Oumuamua had approached from the direction of Vega in Lyra and 2I, Borisov from Cassiopeia, this new arrival came from an entirely different region of the sky. The three confirmed interstellar objects approached from directions separated by roughly 60 to 90 degrees, suggesting that such visitors arrived from all parts of the galaxy rather than from any preferred direction. This omnidirectional arrival pattern had profound implications for understanding the local interstellar environment. Rather than existing within a relatively empty bubble of space, our solar system appeared to be embedded in a complex network of stellar debris flows. Material ejected from dying stars disrupted planetary systems and gravitational interactions throughout the local galaxy was constantly flowing through our cosmic neighborhood. The galactic context provided even more perspective on 3I-ATLAS's journey. Our solar system orbits the galactic center at approximately 220 kilometers per second, completing one orbit every 225 million years. During its presumed million-year journey through interstellar space, 3I-ATLAS would have encountered the wakes and gravitational influences of dozens of stellar systems, each slightly altering its trajectory and velocity. The object's composition offered additional clues about its origin. Spectroscopic analysis revealed a surface dominated by silicate minerals and organic compounds with isotope ratios that differed subtly but measurably from materials found in our solar system. These chemical signatures suggested formation around a star with different metallicity than our Sun, possibly an older star with fewer heavy elements, or a younger star enriched by previous generations of stellar evolution. Perhaps most intriguingly, the object's approach angle relative to the galactic plane suggested it had spent much of its journey traveling through the galactic thick disk, a population of older stars with different chemical compositions and kinematics than the compositions. Thin disk where our Sun resides. This implied that 3I-ATLAS might carry samples of materials from a very different epoch of galactic evolution. The trajectory also revealed information about the object's future. After its October encounter with the Sun, 3I-ATLAS would begin a gradual acceleration back toward interstellar space, eventually reaching an escape velocity that would carry it beyond the outer planets by early 2026. Computer models predicted it would exit the solar system in the direction of the constellation Perseus, beginning another million-year journey through the galaxy. But unlike its inbound trajectory, which had been shaped by the gravitational influences of dozens of stellar encounters, the object's outbound path would be relatively predictable for the next several thousand years. It would carry with it subtle changes in composition and structure caused by its encounter with solar heating and radiation, modifications that might be detectable by hypothetical alien astronomers if 3I-ATLAS eventually passes through another planetary system. The mathematical precision of orbital mechanics allowed astronomers to predict the visitor's position months in advance, enabling coordinated observation campaigns that would have been impossible with Oumuamua. Ground-based telescopes could be scheduled well in advance. Space missions could theoretically be planned to intercept the object during its closest approach. The European Space Agency even conducted preliminary studies of a rapid response probe that could potentially rendezvous with 3I-ATLAS during its passage through the inner solar system. As the object continued its approach toward perihelion, its trajectory became a cosmic timeline that connected the present moment to events that occurred when our ancestors were first learning to walk upright on the African savanna. 3I-ATLAS had been traveling through interstellar space for longer than human civilization had existed, carrying with it samples of materials that predated our species. The path of this particular outsider illuminated the dynamic nature of the galaxy itself. Far from being a static collection of isolated stellar systems, the Milky Way revealed itself as a complex ecosystem where material constantly flowed between stars, carrying information about conditions in distant regions of space and time. Every measurement of 3I-ATLAS's position and velocity added another data point to humanity's growing understanding of how matter moves through interstellar space. The object's trajectory was more than just a mathematical curiosity. It was a record of galactic history written in the language of celestial mechanics, a story that began millions of years ago around an alien star and would continue long after our own sun had exhausted its nuclear fuel. The cosmic wanderer continued its billion-year odyssey, temporarily illuminated by our sun's light, carrying secrets from the depths of space and time that we were only beginning to learn how to read. Part 7. Signals in the Noise. Data from 2 visitors, 3 interstellar visitors, 3 completely different personalities. As 3I-ATLAS continued its approach through the solar system, astronomers found themselves comparing its behavior to its enigmatic predecessors, searching for patterns that might reveal universal truths about the nature of objects that drift between the stars. The contrasts were striking and immediate. Where Oumuamua had remained stubbornly inert throughout its passage, showing no signs of the gas and dust emission typical of comets, 3I-ATLAS began outgassing vigorously while still beyond the orbit of Jupiter. Its expanding coma of sublimated materials created a fuzzy envelope roughly 50 kilometers across, larger than the planet Mercury. 2I, Borisov, discovered in 2019, had provided the middle ground between these extremes. That visitor had behaved like a relatively normal comet, complete with the characteristic tail of gas and dust heated by solar radiation. But its chemical composition revealed exotic properties, concentrations of carbon monoxide that exceeded anything found in our solar system's comets by factors of 10 to 50. Dr. Alan Fitzsimmons from Queen's University Belfast, who had studied all 3 visitors, captured the scientific community's bewilderment. It's like receiving 3 postcards from different countries, written in completely different languages, but all claiming to describe the same basic experience of travel. The morphological differences were profound. Oumuamua's extreme elongation, possibly 10 times longer than wide, had no parallel among objects in our solar system. Its tumbling rotation and mysterious acceleration remained unexplained despite years of analysis. Computer models struggled to identify any natural process that could produce such an unusual shape while maintaining structural integrity over millions of years of interstellar travel. 3I-ATLAS, by contrast, appeared refreshingly normal in its basic geometry. Light curve analysis suggested a roughly spherical nucleus with only modest elongation, perhaps 1.5 to 2 times longer than wide. Its rotation period of approximately 29 hours was consistent with what might be expected from a typical comet, and its axis of rotation remained stable rather than tumbling chaotically through space. The chemical signatures told equally diverse stories. Spectroscopic analysis of 2I, Borisov had revealed water vapor, carbon monoxide, and cyanide, a composition broadly similar to comets from the outer reaches of our solar system, but with significant differences in ratios and concentrations. The object had clearly formed in the cold outer regions of an alien planetary system, probably around a star, similar to our Sunday 3I-ATLAS, displayed yet another chemical personality. Its spectrum showed strong signatures of silicate minerals, suggesting a rocky core overlaid with volatile ices. The isotope ratios of hydrogen, oxygen, and carbon differed measurably from solar system values, indicating formation around a star with different metallicity and evolutionary history. Most intriguingly, organic compounds detected in the object's coma included complex molecules that had been modified by millions of years of cosmic ray bombardment. The rotation characteristics provided additional insights into each object's history and structure. Oumuamua's chaotic tumbling suggested either a recent violent collision or an internal structure that departed significantly from simple assumptions about homogeneous density. The 8-hour rotation period was unusually rapid for such an elongated object, requiring either unusual material strength or internal support structures. 2Y. Borisov had exhibited a more conventional rotation period of roughly 7 to 8 hours, with variations in brightness that suggested an elongated but not extremely distorted shape. The object's behavior had been predictably comet-like throughout its passage through the solar system. 3I-ATLAS fell between these extremes, with its 29-hour rotation period and relatively stable axis orientation. The slower rotation suggested either a larger size or more structurally robust construction than its predecessors. Subtle variations in outgassing rates synchronized with the rotation period indicated that volatile materials were not uniformly distributed across the surface, a characteristic that might preserve information about the object's 4T. Formation environment. The outgassing behaviors provided perhaps the most dramatic contrasts between the three visitors. Oumuamua's lack of any detectable coma or tail had been one of its most puzzling characteristics. Despite approaching to within 0.25 astronomical units of the Sun, close enough to vaporize water ice and other volatiles, the object had remained stubbornly inert. This apparent absence of volatile materials had contributed to speculation about artificial construction or exotic composition. 2.1. Borisov had displayed vigorous outgassing throughout its passage, creating spectacular tails visible to amateur telescopes and providing abundant material for spectroscopic analysis. The comet's activity had peaked during its closest approach to the Sun and gradually declined as it moved back toward interstellar space, exactly the behavior predicted by theoretical models. 3I-ATLAS represented yet another variation on the theme. Its outgassing had begun at unusually large distances from the Sun, suggesting either a composition dominated by extremely volatile materials or a surface structure that facilitated rapid sublimation. The coma displayed complex temporal variations that didn't correlate simply with solar heating, hinting at internal processes or structural complexities not seen in typical comets. The speed differences among the three visitors provided clues about their respective origins and ejection mechanisms. Oumuamua's approach velocity of approximately 26 km per second suggested a relatively gentle ejection from a nearby stellar system, possibly through gravitational interactions with giant planets. 2y. Borisov's intermediate velocity of around 32 km per second implied either a more distant origin or a more energetic ejection process. 3I-ATLAS's extreme approach velocity of 61 km per second required either ejection during a catastrophic event, such as a stellar explosion or close encounter with a massive object, or acceleration over vast distances during an extraordinarily long journey through interstellar space. The high velocity suggested origins in regions of the galaxy with different stellar dynamics than our local neighborhood. Population statistics derived from the three discoveries painted an intriguing picture of the interstellar medium. The detection rate suggested that similar objects passed through the inner solar system several times per decade, with most remaining undetected due to their small size or unfavorable viewing geometry. Extrapolating to the entire galaxy implied a vast population of wandering debris, perhaps trillions of objects larger than 100 meters drifting between stellar systems. The diversity of characteristics among just three objects hinted at an even greater range of properties in the broader population. Computer models predicted that future surveys might detect visitors ranging from tiny rocky fragments to massive ice balls hundreds of kilometers in diameter. Some might be pristine samples of primordial solar system material, while others could be heavily processed debris from stellar explosions or planetary collisions. Dr. Robert Werrick, who had the remarkable distinction of discovering 2 of the 3 confirmed interstellar visitors, reflected on the implications. We've gone from 0 to 3 detections in less than a decade. Each one has been completely different from the others, which suggests the total population is far more diverse than we ever imagined. We're sampling objects from all over the galaxy, each carrying its own unique story of formation, evolution, and ejection. The combined dataset from all 3 visitors was already reshaping theoretical models of planetary system formation and evolution. The chemical differences indicated that stellar systems throughout the galaxy had experienced diverse evolutionary histories, with different patterns of planet formation, migration, and disruption. The variety of ejection velocities suggested that multiple mechanisms were responsible for populating interstellar space with debris. Perhaps most significantly, the regular arrival rate implied that material exchange between stellar systems was an ongoing process rather than a rare catastrophic event. The galaxy was revealing itself as a dynamic ecosystem where matter constantly flowed between stars, carrying information about conditions in distant regions of space and time. As 3I-ATLAS continued its approach toward the Sun, adding daily to the growing database of interstellar visitor characteristics, one fact became increasingly clear. These three objects were merely the beginning of a much larger story. The space between stars was not empty, but populated by countless messengers carrying samples from every corner of the galaxy. Each new detection would add another piece to the puzzle, gradually revealing the true nature of interstellar space and our solar system's place within the broader galactic community. Part 8. The probability problem. The mathematics were troubling. That was the polite way astronomers described the growing discrepancy between theoretical predictions and observed reality. Before Oumuamua's surprise arrival in 2017, the most sophisticated models predicted that detectable interstellar objects should pass through the inner solar system perhaps once per century, if we were extremely lucky. 3 confirmed detections in less than 8 years suggested those models were wrong by factors of 10 to 100. Dr. Alan Stern, from the Southwest Research Institute, had spent decades refining calculations of interstellar object populations. His pre-2017 estimates, considered optimistic at the time, predicted roughly 1 detection per decade using the most sensitive survey telescopes then available. We weren't just wrong, he admitted during a 2025 conference presentation. We were spectacularly, embarrassingly wrong. The problem lay in fundamental assumptions about how planetary systems form, evolve, and ultimately eject material into interstellar space. Traditional models assumed that such ejection events were relatively rare, occurring primarily during the late heavy bombardment period when giant planets migrated to their final orbits. These calculations suggested that most stellar systems would contribute only modest amounts of debris to the interstellar medium, but the discovery rate implied something far more dramatic. Either ejection events were much more common than predicted, or the efficiency of these events in producing detectable debris was vastly underestimated. The implications extended far beyond astronomy. They touched on fundamental questions about the structure and evolution of the galaxy itself. The revised estimates were staggering. If Oumuamua, 2I, Borisov, and 3I-ATLAS represented a typical sampling of the interstellar object population, then our solar system should encounter dozens of similar visitors each year. Most would be too small, too dark, or positioned too unfavorably to detect with current technology, but a significant fraction should be within reach of next-generation survey instruments. Extrapolating to the entire galaxy produced numbers that challenged comprehension. The Milky Way might contain trillions of interstellar objects larger than 100 meters in diameter, drifting between stellar systems in a vast network of gravitational interactions. This invisible population would represent a previously unknown component of galactic mass, possibly comparable to the total mass of all planets in all stellar systems combined. The detection statistics provided additional puzzles. All 3 confirmed interstellar visitors had been discovered by relatively small ground-based telescopes operating automated survey programs. This suggested that larger, more sophisticated instruments might detect such objects routinely, perhaps several times per year, once dedicated search programs became fully operational. Dr. Robert Jediker from the University of Hawaii, who specialized in solar system population statistics, described the implications. "We're like people who spent years looking for rare birds and never saw one, then suddenly spotted 3 different species in a single week. Either we got incredibly lucky, or these rare birds are actually everywhere and we just didn't know where to look." The probability calculations became increasingly complex when accounting for observational biases. Interstellar objects were most easily detected when their trajectories brought them relatively close to Earth, and when they were moving slowly enough for repeated observations. Objects approaching from certain directions might be lost in the glare of bright stars, or obscured by the plane of the Milky Way. Monte Carlo simulations attempted to model these selection effects, generating millions of hypothetical interstellar visitors with random properties and trajectories, then determining what fraction would be detectable by existing survey programs. The results consistently indicated that the observed detection rate could only be explained if the true population was orders of magnitude larger than previously estimated. The origins of this vast population remained mysterious. Current theories for planetary system formation predicted ejection rates that were insufficient to populate interstellar space so densely. Several new mechanisms were proposed to account for the discrepancy. Stellar close encounters might be more disruptive than previously assumed. When stars pass within a few thousand astronomical units of each other, events that occur roughly once every few million years for a typical stellar system, the gravitational perturbations could eject not just individual objects, but entire populations of comets and asteroids. Binary star evolution provided another potential source of interstellar debris. Roughly half of all stars exist in multiple star systems, where complex gravitational interactions during stellar evolution could destabilize planetary orbits and eject material at high velocities. The breakup of wide binary systems might scatter debris across vast regions of interstellar space. More exotic scenarios involved the death throes of massive stars. Supernovae and other stellar explosions could blast entire planetary systems into interstellar space, creating waves of high-velocity debris that would eventually encounter other stellar systems millions of years later. The chemical composition and extreme velocities of some interstellar visitors supported this possibility. The concept of gravitational focusing provided yet another explanation for the apparent abundance of interstellar objects. The Sun's gravity would bend the trajectories of passing objects, concentrating them into the inner solar system where they could be more easily detected. This focusing effect might make our solar system a preferential target for interstellar visitors, creating an artificially high detection rate. Perhaps most intriguingly, some researchers proposed that we might be witnessing the aftermath of galactic evolution on much larger scales. The Milky Way's spiral structure, bar-shaped central bulge, and ongoing interactions with satellite galaxies could create tidal forces that periodically disrupt stellar systems throughout the galaxy. These events might occur in waves separated by hundreds of millions of years, filling interstellar space with debris during certain epochs of galactic evolution. The timing of humanity's first interstellar object detections raised additional questions. Why were these discoveries occurring now, during the brief period of our species' technological development? The anthropic principle suggested that this timing might not be coincidental. Perhaps we existed during a period of enhanced interstellar debris flux, possibly related to our solar system's current position within the galaxy's spiral structure. Dr. Abraham Loeb from Harvard University, who had become a prominent advocate for considering artificial explanations for interstellar objects, offered a different perspective. The abundance of these visitors might not be a statistical anomaly. If technological civilizations are common, and if they occasionally launch probes or artifacts into interstellar space, then what we're observing could be a combination of natural debris and artificial messengers. This technological hypothesis remained controversial, but the detection statistics provided some support. If even a tiny fraction of the inferred interstellar object population consisted of artificial artifacts, the probability of detecting such objects during humanity's brief technological era would be significantly enhanced. The unusual properties of some visitors, particularly Oumuamua's extreme elongation and mysterious acceleration, remained unexplained by conventional natural processes. The implications extended beyond astronomy to astrobiology and the search for extraterrestrial intelligence. If interstellar space was indeed populated by countless wandering objects, then biological material might routinely travel between stellar systems, potentially spreading life throughout the galaxy. Complex organic molecules detected in some interstellar visitors supported this possibility. The probability problem also affected practical considerations for planetary defense. If large interstellar objects passed through the inner solar system several times per decade, then statistical calculations for impact hazards needed to be revised. While the probability of any individual object striking Earth remained extremely low, the cumulative risk over geological timescales might be higher than previously estimated. As survey telescopes continued their nightly vigil, detecting candidate interstellar objects with increasing frequency, the true scale of the probability problem became clear. The universe was not the sparse, nearly empty space between stars that previous generations had imagined. Instead, it revealed itself as a dynamic, crowded environment where material constantly moved between stellar systems, connecting distant worlds through networks of gravitational interaction that operated over millions of years. The mathematics of chance had been rewritten by observation, forcing humanity to confront a cosmos far more active and interconnected than we had ever dared to imagine. The space between stars was alive with wanderers, and we were finally learning to recognize their signatures among the cosmic noise. Part 9. The Fermi Paradox Revisited. Where is everybody? Enrico Fermi's famous question, posed during a casual lunch conversation in 1950, took on entirely new dimensions as humanity grappled with the implications of routine interstellar visitors. If the galaxy was filled with wandering debris from countless stellar systems, why weren't we also encountering evidence of the civilizations that might have created some of it? The classic Fermi paradox had always been built on assumptions of vast, empty distances between stars. Even if the galaxy contained millions of technological civilizations, the argument went, the sheer scale of interstellar space made contact virtually impossible. Radio signals would weaken to undetectable levels across such distances. Physical travel would require resources and timeframes that even advanced civilizations might find prohibitive. But the discovery of Oumuamua, 2I, Borisov, and 3I-ATLAS had fundamentally altered this picture. The space between stars was not empty, but filled with a constant stream of messengers carrying information between stellar systems. If natural objects could make these journeys routinely, why not artificial ones? The detection statistics suggested that objects larger than 100 meters passed through the inner solar system several times per decade. Extrapolating to smaller sizes implied that debris from other stellar systems was constantly raining down on Earth, perhaps thousands of tiny fragments each year, most too small to detect or survive atmospheric entry. This revelation transformed the Fermi paradox from a question about the absence of signals to a question about the nature of the signals we might already be receiving. What if extraterrestrial civilizations had been communicating with us for millennia, not through radio transmissions, but through physical artifacts designed to survive the journey between stars? Dr. Abraham Loeb from Harvard University had become the most prominent advocate of this perspective. "We've been listening to the sky for radio signals for decades," he argued, "but we've been ignoring the possibility that advanced civilizations might prefer to send physical messages. A well-designed artifact could carry far more information than any radio signal, and it would arrive at its destination with guaranteed delivery." The concept of interstellar messaging through physical objects wasn't new. Science fiction had explored such ideas for decades, and serious scientists had occasionally proposed theoretical designs for Bracewell probes, self-replicating artifacts that could propagate throughout the galaxy, carrying information between civilizations. But the abundance of interstellar visitors suggested that such messaging might be not just possible, but routine. If every technological civilization occasionally launched artifacts into interstellar space, whether intentionally or as byproducts of their industrial activities, then the galaxy might be filled with artificial messengers awaiting discovery and interpretation. The challenge lay in distinguishing artificial objects from natural ones. Oumuamua's unusual properties had sparked intense debate about its possible artificial origin. Its extreme elongation, mysterious acceleration, and lack of detectable outgassing were difficult to explain through natural processes alone. Yet, the scientific community had largely settled on exotic but natural explanations rather than entertaining the possibility of technological origin. This resistance to artificial explanations reflected deep-seated biases within scientific culture. The principle of Occam's razor suggested that natural explanations should be preferred over more complex artificial ones. The burden of proof for extraordinary claims, such as the detection of alien technology, was set appropriately high to prevent false discoveries and maintain scientific credibility. But the statistical abundance of interstellar visitors was forcing a reconsideration of what constituted the simpler explanation. If such objects were rare natural phenomena, their detection during humanity's brief technological era represented an extraordinary coincidence. If they included artificial artifacts from technological civilizations, their abundance during our era of detection capability might be less surprising. The timing argument was particularly compelling. Humanity had developed the capability to detect interstellar objects only within the past few decades. The fact that we discovered 3 such objects within our first 8 years of systematic searching suggested either remarkable luck or a population density much higher than predicted by natural processes alone. Dr. R.V. Loeb calculated the probabilities. If interstellar objects like Oumuamua are purely natural phenomena with the abundance implied by our detection rate, then the probability of humanity encountering them during our brief technological era is roughly 1 in 10,000. Such coincidences are possible, but they should make us consider alternative explanations. The search for extraterrestrial intelligence had already begun adapting to these possibilities. Radio telescopes now routinely examined newly discovered interstellar objects for any signs of artificial signals. Optical observatories searched for unusual reflectivity patterns that might indicate manufactured surfaces. Even gravitational wave detectors were being considered as tools for identifying very massive artificial objects. The European Space Agency had proposed an ambitious mission to intercept the next suitable interstellar visitor with a high-speed probe capable of detailed analysis. Such a mission could determine whether apparently natural objects contained hidden artificial components, embedded computers, communication devices, or even biological samples from their civilizations of origin. The implications extended beyond the search for current civilizations to questions about the archaeological record of galactic intelligence. If technological species had been launching artifacts into interstellar space for millions of years, then some of these messengers might represent the only remaining traces of long-extinct civilizations. The galaxy could be filled with the technological fossils of species that had risen and fallen long before our sun even formed. This galactic archaeology perspective suggested that interstellar objects might preserve information about the long-term evolution of intelligence in the Milky Way. Artificial artifacts could contain data about the technologies, cultures, and ultimate fates of civilizations that had existed billions of years in the past. The chemical and structural analysis of such objects might reveal patterns in how intelligence developed and spread throughout the galaxy. The concept also raised questions about humanity's own contributions to interstellar debris. Our space activities were already creating artifacts that would eventually escape the solar system and drift between the stars. The Voyager probes, New Horizons, and various other spacecraft would become Earth's first interstellar ambassadors, carrying information about our civilization to whatever intelligence might eventually encounter them. More problematically, human space activities were also generating significant amounts of debris that might eventually reach interstellar space. Spent rocket stages, defunct satellites, and fragments from orbital collisions could become part of the galactic population of wandering objects. Future archaeologists studying debris from our stellar neighborhood might conclude that 21st century Earth was populated by a wasteful, short-sighted species that polluted even the space between stars. The philosophical implications were profound. If the galaxy was indeed filled with artificial messengers from countless civilizations, then the Fermi paradox might be resolved not through the absence of extraterrestrial intelligence, but through our failure to recognize its presence. The answer to "where is everybody?" might be "all around us," in forms we're only beginning to understand. This perspective suggested that the search for extraterrestrial intelligence needed to expand far beyond radio astronomy to include the systematic study of interstellar visitors. Every object that entered our solar system from interstellar space represented a potential message from another world, encoded in its structure, composition, trajectory, and behavior. The challenge was developing the tools and techniques to decode such messages. Unlike radio signals, which were designed to be obviously artificial, physical artifacts from alien civilizations might be designed to appear natural to avoid detection by hostile intelligences. The distinction between advanced technology and exotic natural phenomena might be subtle enough to escape current analytical methods. As surveys continued detecting new interstellar visitors with increasing frequency, the revised Fermi paradox became a question not of silence but of interpretation. The galaxy might be constantly communicating with us through physical messengers that we were only beginning to recognize and understand. The cosmic loneliness that had characterized humanity's view of the universe since the scientific revolution was giving way to a growing awareness of our participation in a vast, ancient network of material exchange between stellar systems. Whether that network included intentional messages from other intelligences remained an open question, but the possibility was transforming both our search strategies and our fundamental assumptions about our place in the cosmos. The answer to Fermi's question might be, "They're here, we're just learning how to notice them." Part 10 Theories, Tensions. The coffee had grown cold hours ago, but Dr. Sarah Chen continued staring at the data streaming across her monitor at the Jet Propulsion Laboratory. The latest spectroscopic observations of 3I-ATLAS showed something that shouldn't exist: isotope ratios that defied every model of stellar nucleosynthesis she could imagine. Either the object had formed under conditions unlike anywhere else in the known universe, or the models themselves needed fundamental revision. The scientific community's response to mounting anomalies in interstellar visitor data had polarized into increasingly entrenched camps. On one side stood the methodological conservatives, insisting that natural explanations must be exhausted before entertaining more exotic possibilities. On the other, a growing group of researchers argued that the accumulating evidence demanded consideration of hypotheses that previous generations would have dismissed as science fiction. The debate had grown particularly intense around Oumuamua's persistent mysteries. 8 years after its discovery, the object's extreme elongation and mysterious acceleration remained unexplained by any convincing natural mechanism. Computer simulations had tested every conceivable formation scenario: tidal disruption near massive stars, collisional fragmentation in dense stellar clusters, exotic sublimation processes, yet none could account for all of the object's observed properties. Dr. Alan Fitzsimmons from Queen's University Belfast, one of the most respected voices in asteroid and comet research, defended the conservative position. Science progresses by finding natural explanations for natural phenomena. The history of astronomy is littered with mysterious objects that seem to require exotic explanations until we understood them better. Oumuamua may be unusual, but unusual isn't synonymous with artificial. The natural explanation camp had rallied around increasingly sophisticated models. Perhaps Oumuamua was composed of solid hydrogen, sublimating so slowly that its outgassing remained invisible to our instruments. Maybe it was a fragment of a nitrogen iceberg, similar to the surface composition of Pluto, but ejected into interstellar space by some catastrophic event. These explanations required exotic conditions and materials, but they remained within the bounds of known physics and chemistry. The artificial hypothesis camp, led by Dr. Abraham Loeb, argued that the natural explanations had become so contrived that they strained credibility more than the technological alternative. When you need to invoke invisible outgassing, exotic materials that don't exist anywhere else in the solar system, and formation mechanisms that have never been observed, Loeb argued, perhaps it's time to consider the possibility that we're looking at technology. The debate had taken on philosophical dimensions that extended far beyond the specific case of any individual object. It touched on fundamental questions about the nature of scientific inquiry, the burden of proof for extraordinary claims, and the role of intellectual conservatism in preventing both false discoveries and genuine breakthroughs. Dr. Michelle Bannister from the University of Canterbury represented a moderate position. The real issue isn't whether any specific object is natural or artificial. The issue is that we're seeing phenomena we don't understand, which means our models of planetary formation, stellar evolution, and interstellar chemistry are incomplete. Whether the answers involve exotic natural processes or extraterrestrial technology, we're clearly missing something important. The tensions had been exacerbated by the media coverage surrounding interstellar visitor discoveries. Headlines screaming "alien probe" and "visitors from space" had forced scientists into defensive positions, emphasizing conventional explanations to avoid accusations of sensationalism. This defensive posture had created a climate where researchers were reluctant to discuss artificial possibilities, even in private conversations. The situation had historical precedents. During the early days of pulsar astronomy, the incredibly regular radio signals from these objects had been nicknamed LGMs, little green men, because no known natural process could produce such precise timing. Only after discovering multiple pulsars with similar properties did astronomers become confident that they were observing a new type of stellar remnant rather than alien technology. But the interstellar visitor situation was complicated by the object's transient nature. Unlike pulsars, which could be observed repeatedly over years or decades, interstellar objects provided only brief windows for detailed study. Oumuamua had been observable for mere weeks before fading beyond the detection limits of Earth's most powerful telescopes. This temporal constraint made it extremely difficult to gather the comprehensive data needed to resolve debates about the object's nature. The scientific culture itself had become part of the problem. Peer review processes favored incremental advances in understanding over revolutionary paradigm shifts. Grant committees were reluctant to fund research into exotic explanations when more conventional alternatives remained unexplored. Career advancement depended on publishing results that built logically on previous work rather than challenging fundamental assumptions. Young researchers found themselves caught between competing pressures. The most interesting and potentially career-defining discoveries lay in exploring unconventional explanations for anomalous data. But the safest path to academic success involved working within established frameworks, even when those frameworks struggled to explain the observations. Dr. Jennifer Bergner from UC Berkeley, whose research focused on the chemistry of interstellar objects, described the dilemma. I've seen junior faculty members self-censor their own hypotheses because they're afraid of being labeled as fringe scientists. We're creating an environment where the most important questions can't be discussed openly because they might damage someone's reputation. The international nature of modern astronomy added another layer of complexity. Researchers from different countries brought varying cultural attitudes toward unconventional ideas. European scientists tended to be more conservative in their interpretations, while American researchers were more willing to speculate publicly about exotic possibilities. Asian astronomers often found themselves mediating between these approaches. Social media had amplified these cultural differences, allowing debates that might once have remained confined to scientific conferences to spill over into public forums. Twitter threads about Oumuamua's artificial origin garnered thousands of retweets, while careful analyses of natural formation mechanisms received minimal attention outside professional circles. The polarization had practical consequences for observational programs. Telescope time allocation committees found themselves navigating between proposals that assumed conventional explanations and those that explicitly searched for signs of artificial origin. Some facilities developed informal policies against funding research that specifically looked for evidence of extraterrestrial technology, preferring to support investigations that could produce publishable results, regardless of their findings. The debate had also revealed interesting generational divides within the astronomical community. Established researchers who had built their careers on conventional models tended to resist explanations that might invalidate decades of previous work. Younger scientists, with less invested in existing paradigms, were more open to revolutionary possibilities. Dr. Robert Werrick, who had discovered both Oumuamua and 3I-ATLAS, found himself in the unusual position of having detected phenomena that challenged his own theoretical expectations. Quote, "When you spend your career looking for conventional asteroids and comets, then suddenly find objects that don't fit any known category, it forces you to question everything you thought you understood about the solar system." The accumulating data from multiple interstellar visitors was gradually shifting the terms of the debate. Each new detection provided additional constraints on theoretical models, making it increasingly difficult to construct natural explanations that could account for the full range of observed properties. Yet the same data could also be interpreted as evidence for a diverse population of artificial artifacts with different designs and purposes. Perhaps most significantly, the debate was forcing the scientific community to confront its own biases and assumptions about what constituted reasonable explanations for astronomical phenomena. The boundary between exotic natural processes and simple artificial ones was proving far less clear than anyone had anticipated. Late-night conversations at astronomical conferences increasingly focused on questions that would have seemed absurd just a decade earlier. How would we recognize alien technology if we encountered it? What observational signatures would distinguish artificial objects from extremely unusual natural ones? How should the scientific community respond if the evidence for extraterrestrial intelligence became overwhelming? These were not just academic questions. As survey telescopes continued detecting new interstellar visitors with increasing frequency, astronomers found themselves analyzing data that challenged fundamental assumptions about the nature of matter, the evolution of planetary systems, and humanity's place in the cosmic order. The theories and tensions surrounding interstellar visitors reflected deeper uncertainties about the universe we inhabited. Whether the answers lay in exotic physics or extraterrestrial technology, one fact was becoming clear. The cosmos was far stranger and more dynamic than the neat theoretical models of previous generations had suggested. The debate continued in laboratories and conference rooms around the world. But outside those heated discussions, the objects themselves continued their ancient journeys through interstellar space, carrying secrets that humanity was only beginning to learn how to interrogate. Part 11. The next discovery could change everything. The future of interstellar visitor detection was arriving ahead of schedule deep in the Chilean Andes, the Vera Sea. Rubin Observatory was completing its final tests months earlier than planned, driven by the urgent need to catalogue the cosmic messengers streaming through our solar system. When fully operational, this technological marvel would revolutionize our ability to detect and study visitors from other star systems. The observatory's 4-meter mirror and 3 billion pixel camera would scan the entire visible sky every 3 days, generating roughly 20 terabytes of data each night. More importantly, it would do so with unprecedented sensitivity, capable of detecting objects as faint as 24th magnitude, approximately 40 million times dimmer than the faintest stars visible to the naked eye. Dr. Mario Juric, who directed the observatory's data management systems, described the transformation this would bring. We're going from catching maybe one interstellar visitor per decade to potentially detecting dozens per year. Instead of scrambling to study objects as they're leaving the solar system, we'll be tracking them from the moment they arrive. The implications were staggering. Current detection methods relied on luck and favorable geometry. Objects had to pass relatively close to Earth, while bright enough for existing surveys to notice them. The Rubin Observatory would cast a much wider net, finding visitors while they were still approaching the inner solar system and providing months or years of advance warning before their closest approach. But detecting these cosmic wanderers was only half the challenge. The real revolution would come from the observatory's ability to characterize large populations of interstellar objects, revealing patterns that individual discoveries could never provide. Statistical analysis of hundreds or thousands of visitors would finally answer fundamental questions about their origins, compositions, and the mechanisms that ejected them from their parent star systems. Artificial intelligence systems were being developed specifically to recognize the subtle signatures of interstellar motion among the billions of moving objects the observatory would detect each night. Machine learning algorithms trained on simulated data would learn to distinguish hyperbolic trajectories from the elliptical orbits of conventional solar system objects, flagging potential interstellar visitors within hours of their first detection. The European Space Agency was preparing complementary systems that would automatically trigger follow-up observations at telescopes worldwide. Within minutes of confirming a new interstellar visitor, observatories on multiple continents would begin coordinated campaigns to measure its spectrum, rotation, and detailed properties before it faded below the detection threshold. NASA's Jet Propulsion Laboratory had taken the preparation one step further, developing rapid response spacecraft concepts that could potentially intercept particularly interesting visitors. The designs utilized solar sail technology and gravitational slingshot maneuvers to achieve the extreme velocities needed to catch up with objects traveling at dozens of kilometers per second relative to the Sunday Doctor. Julie Castillo-Roges, who led the Interceptor mission studies, explained the technical challenges. We're talking about chasing objects that are moving faster than anything we've ever tried to intercept. The spacecraft would need to be pre-positioned in specific orbits, waiting for targets of opportunity, and then execute complex maneuvers with almost no margin for error. The potential scientific payoff justified these extreme measures. Direct sampling of interstellar visitor material would provide unambiguous evidence of its origin and composition. Microscopic analysis could reveal details about formation conditions in alien planetary systems, the effects of millions of years of cosmic ray bombardment, and possibly even preserved biological materials from other worlds. But perhaps the most tantalizing possibility was the prospect of finding something that couldn't be explained by natural processes. The statistical abundance of interstellar visitors suggested that if even a tiny fraction were artificial artifacts, future surveys should detect them routinely. Unlike the current situation where individual anomalous objects generated endless debate, clear patterns in the data might provide compelling evidence for extraterrestrial technology. The search strategies were expanding beyond conventional optical astronomy. Radio telescope arrays were being programmed to automatically scan newly discovered interstellar objects for any signs of artificial signals. The techniques developed for SETI research, searching for patterns that indicated intelligent origin, would be applied to every visitor that entered our cosmic neighborhood. Infrared space telescopes offered another avenue for discovery. Artificial objects might have thermal signatures that differed from natural ones, particularly if they contained internal heat sources or unusual surface materials. The James Webb Space Telescope had already demonstrated its ability to study solar system objects in unprecedented detail, and similar techniques could be applied to interstellar visitors. Even more exotic detection methods were being explored. Gravitational wave observatories might be sensitive to the passage of very massive interstellar objects, particularly if they had unusual internal structures. Neutrino detectors could potentially identify visitors carrying radioactive materials or even artificial power sources. The implications extended beyond detection to questions of planetary defense. While the probability of any individual interstellar object striking Earth remained extremely low, the discovery that such objects were far more numerous than previously believed had prompted new risk assessments. Computer simulations suggested that large interstellar impactors might occur once every few million years, rare enough to be essentially ignored on human timescales, but frequent enough to have influenced Earth's biological evolution over geological time. More concerning was the possibility of detecting an artificial object on a collision course with Earth. While such a scenario remained purely speculative, it had prompted preliminary discussions about how humanity should respond to clear evidence of extraterrestrial technology, particularly if that technology posed a potential threat. The discovery protocols were being revised to account for these possibilities. Plans were developed for immediate international consultation if any interstellar visitor displayed unambiguously artificial characteristics. The procedures resembled those used for potential asteroid impact scenarios, but with additional considerations for the possibility that the object might be under some form of intelligent control. Academic institutions were establishing new research programs dedicated to interstellar visitor studies. Graduate students could now specialize in a field that hadn't existed a decade earlier, analyzing data from objects that originated around alien stars. The curriculum included not just astronomy and planetary science, but also astrobiology, materials science, and even archaeology, skills that might be needed to interpret artifacts from extraterrestrial civilizations. International cooperation was expanding rapidly. The European Space Agency, NASA, the Japanese Space Agency JAXA, and other organizations were coordinating their future missions to ensure comprehensive coverage of interstellar visitor discoveries. Bilateral agreements established procedures for sharing data and coordinating observations, treating interstellar objects as a common scientific resource for all humanity. Private space companies were also joining the effort. Several firms had announced plans to develop specialized spacecraft for intercepting and studying interstellar visitors. The potential commercial value of such missions remained unclear, but the scientific prestige and technological challenges attracted significant investment. The legal implications were complex and unprecedented. International space law had never contemplated the scenario of studying material that originated in other star systems. Questions arose about ownership rights, contamination protocols, and the responsibilities of different nations if artificial objects were discovered. Legal scholars were developing frameworks for interstellar visitor governance, though they acknowledged that the law would likely lag behind the discoveries. Cultural and philosophical preparations were perhaps equally important. Humanity's first confirmed encounter with material from another star system had already challenged our sense of cosmic isolation. Future discoveries might force even more fundamental reconsiderations of our place in the universe, particularly if artificial objects were found to be common. Religious and philosophical communities were beginning to grapple with the implications of routine contact with extraterrestrial materials. While the objects themselves might be inanimate, they represented tangible connections to other worlds and possibly other forms of intelligence. The psychological and cultural impacts of such discoveries remained largely unexplored territory. As survey telescopes continued their nightly vigils, scanning the sky for the telltale motion patterns of interstellar visitors, the sense of anticipation within the scientific community was palpable. The next major discovery might be months or years away, but it seemed inevitable. The universe had already demonstrated that it was far more dynamic and interconnected than previous generations had imagined. The question was not whether humanity would encounter more interstellar visitors, but what those encounters would reveal about the nature of planetary systems, the frequency of life in the galaxy, and the possibility that intelligence might be a common rather than extraordinary phenomenon. The future was approaching at 50 kilometers per second, carrying with it answers to questions we were only beginning to learn how to ask. Part 12, Closing the Loop. The data streams never stop. Tonight, as you drift towards sleep, robotic telescopes across 6 continents are capturing photons that left distant stars millions of years ago. Among those ancient points of light, algorithms search for the subtle motion that betrays visitors from other worlds. The cosmic messengers continue their billion-year journeys, indifferent to our newfound ability to notice their passage through our small corner of space. We began this story with a simple observation, an object not bound to our sun passing through our cosmic backyard. Now, after following the evidence across 8 years of discovery and debate, we find ourselves confronting a universe that refuses to conform to our expectations. The space between stars is not the empty void our ancestors imagined, but a highway travelled by wanderers carrying messages we are only beginning to decipher. 3 confirmed visitors. Oumuamua, with its impossible shape and mysterious acceleration, tumbling through the dark toward Pegasus. 2Y, Borisov, reassuringly comet-like, yet chemically alien, trailing exotic vapors from a world we'll never see. And 3I-ATLAS, approaching even now with its promise of answers and inevitable new questions. Each object has challenged our understanding in different ways. Each has forced us to expand our conception of what exists in the cosmos and how frequently it visits our doorstep. Yet, for all their differences, they share a common message. The galaxy is far more active and interconnected than we ever dared imagine. The mathematics tell a story that our intuition struggles to accept. If these 3 discoveries represent a typical sampling rate, then dozens of similar objects pass through our solar system each year. Most remain invisible to our instruments, too small, too dark, or positioned too unfavorably for detection. But they are there, carrying with them samples from every type of star system, every epoch of galactic evolution, every mechanism that can fling matter between the stars. This revelation transforms our understanding of Earth's place in the cosmic order. We are not isolated inhabitants of a closed system, protected from outside influence by vast distances and empty space. We are participants in a galactic ecosystem that has been delivering samples to our planet for billions of years. The materials that formed our world include contributions from stellar systems throughout the local region of the Milky Way. The implications cascade through every field of science. Planetary formation models must account for routine contamination by interstellar materials. The origin of life on Earth might involve organic compounds that survived journeys between stars. The evolution of our solar system has been influenced by occasional visitors carrying momentum and energy from distant worlds. But perhaps the most profound implication concerns the Fermi paradox and humanity's search for evidence of extraterrestrial intelligence. The space between stars is not silent and empty, but filled with physical messengers that could carry information more reliably than any radio signal. If technological civilizations exist elsewhere in the galaxy, they might prefer to communicate through artifacts designed to survive million-year journeys between stellar systems. The debate over Oumuamua's possible artificial origin illuminated the challenges we face in recognizing such messages. The boundary between extremely unusual natural phenomena and relatively simple artificial objects may be far less clear than we assume. Our current analytical techniques, developed for studying conventional solar system objects, may be inadequate for identifying technology designed by non-human intelligence. This uncertainty forces us to confront uncomfortable questions about our readiness for contact with extraterrestrial civilizations. If alien artifacts are already passing through our solar system, indistinguishable from exotic natural objects to our current level of analysis, then we may be failing to recognize the very evidence we claim to be seeking. The scientific community's response to these possibilities has revealed both the strengths and limitations of our collective approach to unprecedented phenomena. The methodological conservatism that protects us from false discoveries may also blind us to genuinely revolutionary developments. The peer review processes that ensure rigorous analysis may also suppress investigation of ideas that challenge fundamental assumptions. Yet, the system adapts. Funding agencies now support research into interstellar visitor detection and characterization. New telescopes are being designed specifically to find and study objects from other star systems. International protocols are being developed for coordinating responses to particularly unusual discoveries. The technology revolution is already underway. The Vera-C Rubin Observatory will soon scan the entire sky every few nights, detecting dozens of interstellar visitors each year, rather than the handful we've found so far. Artificial intelligence systems will recognize their signatures within hours of first detection. Rapid response protocols will trigger coordinated observations worldwide. For the first time in human history, we are preparing to study material from other star systems as a routine scientific enterprise rather than an extraordinary event. Graduate students are specializing in interstellar visitor analysis. Research programs are being established at major universities. New scientific journals are being founded to publish the growing volume of research. The cultural transformation may be equally significant. Humanity is slowly adjusting to the reality of living within a galaxy that actively delivers samples from other worlds. The psychological isolation that characterized our species for most of its history is giving way to a growing awareness of cosmic connectivity. This shift is accelerating as detection rates increase, The discovery of 3I-ATLAS generated less media hysteria than Oumuamua's arrival, but deeper scientific excitement. We are becoming accustomed to the idea that our solar system receives regular visitors, even as we struggle to understand what their presence means. The next phase of this story is already being written in the data streaming from telescopes around the world. Statistical analysis of larger samples will reveal patterns invisible in individual discoveries. Detailed studies of composition and structure will illuminate the conditions that exist around other stars. Direct sampling missions may finally provide unambiguous answers to questions about the object's origins and nature. But for all our technological preparations and scientific protocols, the most important discoveries may be the ones that force us to abandon our current frameworks entirely. The universe has already demonstrated its capacity to surprise us. The objects traveling between stars may carry messages encoded in forms we haven't yet learned to recognize. As you close your eyes tonight, consider the vast networks of matter flowing through interstellar space. Fragments ejected by dying stars, debris scattered by planetary collisions, materials shaped by gravitational chaos around alien worlds. All of it in motion, following trajectories that intersect and separate over millions of years, occasionally delivering samples to planetary systems like our own. Some of these wanderers may carry the chemical signatures of life from distant worlds. Others might preserve information about stellar evolution in regions of the galaxy we'll never directly observe. A few could be artifacts created by intelligence we haven't yet learned to recognize. The cosmic messengers continue their ancient journeys, indifferent to our theories and expectations. They carry with them the stories of worlds beyond our imagination, written in the language of physics and chemistry, geology, and perhaps biology. We are finally learning to read these messages, though we understand only the first few words of what may be vast libraries of information. Oumuamua accelerates through the outer solar system, tumbling toward interstellar space at nearly 40 kilometers per second. In approximately 20 years, it will pass within a few light years of the star system Ross 248. If that system harbors intelligence, they may detect this visitor from our cosmic neighborhood and wonder, as we have wondered, about its origin and meaning. 3I-ATLAS approaches its October encounter with the Sun, brightening steadily as volatile materials sublimate from its surface. Telescopes worldwide track its progress, measuring properties that will illuminate conditions around the distant star where it formed millions of years ago. And somewhere in the darkness beyond our detection capabilities, the next messenger is already approaching. Its trajectory was set in motion by events that occurred before our species existed, carrying it across vast distances to this precise moment in space and time when humanity has finally developed the ability to notice its arrival. The age of interstellar visitors has begun. We are no longer alone in this corner of space, no longer isolated observers of a distant cosmos. We are participants in a galactic community that communicates through wandering messengers connected to every star system through networks of gravitational interaction that operate across millions of years. And so, the only question that remains is, what else is already on its way?